Okay, so we left off talking about how perpetual motion machines can exist, but we didn't really get so much to, well, we did kind of talk about why, and that's that the second law of thermodynamics forbids their existence, right, in two ways. First off, that no conversion of energy is 100% efficient, right? So when we're turning potential energy into kinetic energy, okay, or we've got things rolling along a surface, there's going to be friction. Okay, and friction produces heat, which the second law of thermodynamics says needs to move out of the system and into the surroundings. And for something that's not having any more energy put into it, that means it's lost enough energy that it's going to stop. Okay, the other reason the second law of thermodynamics says that these won't exist is they can't actually do anything. As soon as you hook something up to it and they're demanded to do work, they'll stop, because work is a transfer of energy. And if they transfer energy, they'll lose it and they'll stop, because remember, a perpetual motion machine has no input of energy. Once it gets going, it's supposed to go forever, right? But if you make it do any work, it'll stop. Everyone follow? So that's the second law of thermodynamics and how it forbids the existence of these. Now, the second law of thermodynamics is something that we want to harness whenever possible. Because if we know that thermal energy always flows from a hot object to a cold object, we might be able to put something in the middle and make it do useful work. Okay, this flow of energy from hot to cold could be used to do useful work. Okay, that's the idea behind a heat engine. Right? A heat engine wants to harness that flow of energy from hot to cold and make it do useful work. So that's what we see here in this diagram. Okay, we got the high temperature area here where we got tons and tons of thermal energy. Okay, and heat is going to this theoretical heat engine here. Right, and in that heat engine, okay, some of that thermal or transfer of thermal energy is going to be used to do useful work. Right, that could be like a propeller blade or something like that. Okay, and then a lot of it is still going to go straight through to the low temperature area. Okay, what's going to be the key to making something like that work? If you want to get a lot of energy moving from hot to cold, what's the key to doing that? Okay, let me put it this way. If you have a big old electric heater sitting right in front of you and it's on and it's pumping out heat and you put your hands in front of it, do you notice that it's quite hot? Okay, now if I put, let's say, a person there instead of the heater and you put your hands that same distance away from the person, why don't you feel anything? No, it's not that they're blocking it. I've replaced the heater with the person. They don't produce as much heat. They're the same temperature you are within a degree or so. All right. So I mean, if they had a fever, then you might right, they feel hot, right? Because you can tell that when someone's got a fever, they are noticeably warmer. Okay. That's why your mom goes, puts the back of her hand on your head to see if you have a fever, right? Because her hand is colder than your head. If she notices that your head is hotter than she is, you have a fever. Okay. If she puts her hand on your head and she's like, well, you're not sick. Quit fake and go to school. Okay, it's because she doesn't feel heat coming off of you. Right? If she doesn't feel heat coming off you, it's because you're the same temperature. So for this to work, you need really, really high and comparatively really, really low. That means more energy flows. Okay, the bigger the difference is between the two, the more energy flows. As soon as they're the same temperature, the energy flow is back and forth equally because we achieved a state of equilibrium. Right? So a heat engine only works as long as there's a big differential in the temperature of the two spots. Okay, so for a heat engine, okay, we take this flow from high temperature to low temperature. Okay, that heat, okay, can be converted into mechanical energy, and that can do work. Okay, so a heat engine basically converts heat, okay, or the transfer of thermal energy into mechanical energy. Okay, but it's not, again, 100% efficient. And that's the problem with heat engines. Well, it's the problem with anything, but it's a really big problem with heat engines. Converting heat into any other form of energy is the least efficient energy transfer there is. Okay? Heat is essentially thought to be the lowest form of energy because it's the most difficult to turn into anything else, whereas everything else easily turns into heat. Okay, so we generally consider it to be the lowest form of energy. Right? So the remaining heat gets expelled as exhaust and isn't doing useful work. Right? Now, we can see that in anything that's using heat to make mechanical energy. The internal combustion engine, the engine in your car, is a prime example of that. Okay? It uses the detonation, the explosion of gasoline, okay, within the pistons to create a large amount of heat. Right? And that heat causes the gases within the piston to expand, and that pushes the piston down. That's what does the useful work. Right? But what do you get a lot of? Exhaust and heat. All right. Now, a lot of that heat is not actually doing useful work. Right. In fact, about 30% of the energy in your fuel is used to run the cooling system for your engine, so that it doesn't melt down. Okay. That's how inefficient it is. Okay. It is so inefficient to convert heat into mechanical energy that much of the energy gained from that has to be used to keep the heat under control. Right. That's how inefficient it ends up being. Right. Okay, so that's what they're talking about here. In the internal combustion engine, okay, the fuel in the combustion chamber burns at a high temperature, and that causes the piston to move, and that gains mechanical energy. Right? The remaining energy is expelled as heat through the exhaust, partially through the exhaust, but also because throughout the entire engine block, there are pipes and hoses that run engine coolant through, and that coolant takes the energy from the engine block, and then it goes to your radiator, whose job it is to radiate it out into the environment and keep your engine cool. All right? How many of you have actually looked under the hood of your car? Okay. The radiator's right at the front. Okay? It's got a little cap on it. It's right near the front. Don't ever take the cap off if the engine is hot. Okay? Because it will spray boiling coolant all over you. Okay, it actually says right on the cap not to do that, but I'm cautioning you against it. Okay, the coolant gets really, really hot. Okay, also don't drink the coolant. It's green and very sweet, but it's propylene glycol, which will kill you. All right, so and it also you have to be mindful if you have a leak and you have a pet, they'll go over and try and lick the stuff because it's sweet, but it'll kill them. So don't let them do that. Okay, all right. Now this hypothetical temperature difference that we show in this heat engine up here in this diagram, okay, has to be pretty big, right? So the guy who originally came up with this idea, he wanted his heat engine to work like this and power a boat. Okay? He said, I can power a boat for free. All I need to do is build a heat engine. And that just means that I want to have one really, really, really long pipe that goes down really, really deep where the water is cold. And I'll have this other pipe that's right up here near the surface of the ocean where the water is warmer. And the heat will flow up this cold pipe and through the engine and into the warm water. No, it won't. Why not? I mean, theoretically, that should work. Yeah, it's not a huge difference in temperature. Maybe 10 degrees if you had a really long pipe. Okay, but the main problem is that this cold water that's way down here below the screen still already in contact with this warm water? So what's the motivation for it to go through the motor? None. Yeah, it's already doing that. Okay, there's already like currents, convection currents that are going on within the ocean. It's not going to power your boat. Okay, it's just not going to work. So yeah, that idea was kind of debunked pretty quickly, simply because there's not enough of a temperature differential, and secondly, those two things are already in contact with each other. You basically need separate vessels for the hot and the cold if that's going to work. All right. So according to the second law of thermodynamics, probably not a bad idea to highlight that. Okay, heat never flows naturally from cold to hot. Never. All right, it's just like diffusion. Okay, diffusion never goes against the gradient. It always goes down the gradient. Okay, but heat can be made to move from cold to hot. It never does it naturally, but it can be made to do it as long as we put in work. Yeah, as long as we put in energy, we can make it go against the second law. All right, but you have to do work to make that happen. That's what your fridge does and what your air conditioner does. Okay, they're what we call heat pumps, which is the next thing. If you turn the page over. Okay, heat engines and heat pumps. Okay, so your air conditioner is an example of a heat pump. The jet engine is an example of a heat engine. Right? Works really, really well because when you burn jet fuel, which is really just kerosene, that's the stuff they use in camp stoves, okay, it gets pretty hot. right? And if you consider the altitude at which most jets fly, the temperature up there is pretty cold. So if you've got a really big fire and the surroundings are very, very cold, you get a lot of air that wants to go through that engine. All right, and that's exactly the idea behind a jet engine. If you can make this area really, really hot, energy will want to flow through the turbine and out the back. Okay, everyone follow me there? So you're burning fuel, there's an intake of air there. But once the air is taken in and the oxygen from it is burned, you have a hot area with a cold area behind it. And the hot air rushes through the turbine to get to the cold air, and that turns the turbine, which is the mechanical energy we were looking for. Okay, the hotter you can make that fire, the faster the turbine spins, and the faster the air is expelled out the back of the engine, the faster the jet goes. All right. Fighter jet engines have two chambers where they make heat. They have a primary jet engine, and then they have what's called an afterburner. Okay, you can actually see, if you've ever gone to an air show, you can see and hear when the fighter jet kicks in the afterburners. The flames shoot out the back, okay, of the engine, and the plane gets this huge jump of acceleration because it has just radically increased the temperature within the jet engine, and now there's this huge thrust that's produced. Okay, if you were the pilot of that jet, you would be thrown pinned back against the seat. Okay, when you activate those things, it's just a huge burst of speed. Okay. Now, for the heat pump, I'll show you the diagram of how your fridge works here in just a minute. Okay, this was kind of the first thermoelectric kind of engine. All right, it's kind of like Seebeck's thing with the thermoelectric converter. Right, but essentially what they did is they took two beakers. One beaker had 90 degrees Celsius water in it. The other beaker had like 10 degrees Celsius water in it, and they attached the two to an electric motor. Now, because heat, this side here was getting much hotter, the molecules in here moved faster than they did here. That allowed electrons to flow, okay, and run the motor. How long did the motor run for? Right, until the water was the same temperature. Right? This one's going to be gaining energy. I mean, these aren't insulated, right? They're right next to each other. So a lot of heat was just going straight across from the 90 degree to the 10 degree, right? But as they cooled, as soon as they're around the same temperature, okay, this thing just turns slower and slower and slower until it eventually just stops because a state of equilibrium is reached. Okay, everyone follow me there? So as long as you got a big difference, it works okay. But as soon as that difference is gone, it essentially stops, right? Okay. Yeah, I don't think we need to highlight anything else on there. All right, heat pumps though. Okay, heat pumps are important because they essentially allow us to go against the second law of thermodynamics. Okay, so in your fridge, and I think I explained this just briefly on Friday, okay, you have something called a compressor. That's the thing you can actually hear running when the fridge is running. Okay, the compressor does exactly what its name would imply. It compresses the coolant that is in your fridge. So there's these little pipes that run all throughout your refrigerator on the top and on the sides and in the back, okay? And their job is to bring coolant in a gas state, okay, around the refrigerator. The coolant, when it's in a gaseous state, is really, really cold, right? So heat from your food naturally moves to that really, really cold material, right? So second law of thermodynamics says heat from your food goes to the coolant. When the coolant absorbs the heat, though, okay, sorry, the coolant is in a liquid state. Sorry, what was I saying? Gas. The coolant is in a liquid state when it's going through here, okay? When it receives the heat from the food, it turns into a gas. It changes state from liquid to gas. That takes a lot of energy, so it's capable of absorbing a great deal of energy from your food that's inside. Okay? Now, that stuff is turned into a gas and it goes back down to the compressor. Okay? What does the compressor do to it? It turns it back into a liquid by exerting pressure on it, okay? And that's, you can do that, okay, with certain materials that works better than others, but you can even do it with water, okay? If you have a pressure cooker, for example, you can get liquid water inside the pressure cooker to be higher than the boiling point of water because it increases the pressure on it and it'll stay in a liquid form for longer, okay? Well, this stuff, the gas goes into the compressor forces it back into a liquid state. But a liquid can't hold as much energy as a gas. So what happens to all the heat it absorbed? Yeah, it expels it. So the compressor essentially radiates this heat out, and then there's a little fan that blows that heat out through those bottom grates. And that's why you can feel the warm air coming out from underneath your fridge when it's running. That warm air is the heat from your food in the fridge being pumped into the surroundings, all right? Because naturally, obviously, your food at 4 degrees is not going to naturally transfer energy to the room at 20 degrees. Everyone follow there? Okay, so that's how a heat pump works. It's also how you can wreck your fridge, right? If you try and make your fridge cool really hot objects on a regular basis, like let's say you cook a whole big pot of soup and it's still like 80 degrees Celsius, like, oh, well, I'm not going to eat it, throw it in the fridge at 80 degrees. It's going to overwork your fridge, especially if you do that on a regular basis. No, it's taking the heat from the food. The food is hot, right? We want to get that heat out of the fridge so that everything in the fridge remains cold. So it pumps it into the surroundings. Okay. Now, the other thing that can happen is you can wear out your fridge if you leave the doors open. Because now all the heat it just finished pumping out of the fridge is going back into the fridge. If you recall, way back, it's an old episode of The Simpsons now, Homer decided that he opened the fridge one day when it was really hot and he discovered it was cold inside. And he said that was comfortable, so he put a sheet over it, left the doors open, made himself a little tent, okay, with the fridge doors open, and he sat in there. He had everything he wanted. It was cool. He had his, all his food and beer and whatever Homer likes, okay, was all accessible. He thought it was a great idea, except the fridge is pumping the heat it's absorbing back into the tent he built. Right? He's got the whole thing covered and he's sitting right where the exhaust is trying to pump all that extra heat. So the compressor runs constantly until it burns out. Okay? So you can't cool your house with your fridge. Okay? It won't work because that's the whole area it's trying to pump the heat to. Okay? Everyone follow that? Yeah, so it's just not going to work that way. All right. So a heat pump then, okay, it's obviously not, the process isn't natural, so work has to be done by the refrigerator. Okay, so the refrigerator uses electric energy to pump refrigerant through that piping, okay, and then it pumps the remaining heat, okay, out into the environment here, which is kind of what thermal energy is transferred to the air surrounding the refrigerator. Okay. All right. Making sense? Okay. Down below that, there are some questions I want you to answer here. And they are, that one's super important. Okay, so basically everything but 5 and 8. Because we already talked about 11. Okay, it's not possible to cool a room by leaving the fridge open. Okay, we already talked about that. And I'm not worried about 12. Okay, so 2, 3, 4, 7, 9, and 10. I want you guys to do those right now, and then we'll go over them here in a few minutes. Okay, so let's just quickly go through these here, guys. First law of thermodynamics, very simply, energy can't be created and it can't be destroyed. It's the law of conservation of energy, right? Okay. For question number 3, distinction between work and heat. What do they have in common? Right, they're both transfers of energy, but the energy they transfer is different. What is heat transfer? Right? Thermal energy and work transfers, mechanical energy, right? That's what we got to remember about them. Okay, identify whether each of the following is best explained by the first or second law of thermodynamics. A bouncing ball eventually comes to rest on the floor. Is the ball losing energy? It is. So where's that energy going? To the surroundings. Which law is that? Second law. It's coming to rest because it's losing energy to the surroundings. It's the high energy object. The surroundings is the low energy area, so it's naturally moving away. Okay, if we're talking about the first law of thermodynamics, it'd be better explained by something that kept moving for a long time. Okay, all right. B, a metal spoon eventually becomes hot when placed in a pot of boiling water. Also second law, showing that heat flows, or thermal energy flows from hot to cold. Okay, energy cannot be created or destroyed. First law, that is the first law. All right, number 7, okay, second law of thermodynamics. Well, we just said that. Heat flows from hot to cold. Okay, that's basically how it works. Okay, water is observed to condense on the outside of a cold glass. Which way is the heat going? From the air to the glass. The evidence of that is that the water vapor near the glass is losing so much energy that it's condensing from gas to liquid. Okay, that's why it's condensing on the glass. Plus, if the glass is said to be cold, it must be cold compared to the surroundings. Okay, so heat is flowing into the glass. All right, and which law of thermodynamics best describes the following statements? You can't get something for nothing. First law, yeah, energy can't be created, it can't be destroyed. Okay, you can't even get close to getting something for nothing. Second law, yeah, okay, that's perpetual motion machines being forbidden right there. Okay, and a rock will never suddenly jump into the air. First law of thermodynamics, yeah, okay, a rock is not suddenly going to jump into the air because energy can't be created, okay, unless the rock grew legs, which that would be interesting. All right, let's just talk about number 8. You didn't have to do it, but let's just talk briefly here about number 8. 2 sticks are rubbed together and ignite. Is the work being done on the sticks positive or negative? So if it's me that's, got the, I'm holding the one stick and I've got that bow, and so I'm twisting the one stick back and forth, what am I doing? I'm doing work. Where is my energy going? Towards the stick. So from my point of view, the work is negative. From the stick's point of view, it better be positive, otherwise it's not bursting into flame. Okay, it's got to be gaining energy in order for that to happen. All right, and we talked about number 11 already. So okay, so we're good with that. I think that's where yours ends, right? You don't have anything about the development of the engine after that in your notes, right? I cut that part out. Okay, perfect.